Good morning, everyone, and lovely to see you after a couple weeks away. Over here, does anyone know who this is? Has anyone seen the movie Hidden Figures? Okay, Tim, do you want to give us a bit of a recap of what happened in the movie?
Hidden Figures is about the first lunar missions, and specifically the problem they had of trying to calculate their trajectories and timing for the mission. But of course, they didn't have digital computers back then, so they had a lot of people computers, and it's talking about the story of those people computers who often left out of the lunar narrative.
Yeah, and one important thing is a lot of these people were actually black women who were not allowed to be major mission participants under the culture and rules of NASA at the time. And this, in fact, is Katherine Johnson. I'll put a picture back up in a minute, who was born in 1918 and only died a couple of years ago in February 2020. And she was one of the major contributors to the moon landing missions. And she performed many of the vital calculations that were present for all the manned US space missions that we hear so much about. She spent 30 years at NASA in what was known as the Office of Colored Computers, colored being a term at the time used to refer to black people. And computers indeed was the term used to refer to the actual people that performed calculations in the area pre-digital computers for a very long time. However, Katherine Johnson wasn't just satisfied with being a human computer. She later became one of the pioneers of digital computers within NASA. In fact, one of the things she did with the digital computers was calculating the trajectory for the Apollo 11 mission that is so well known. And so what we're going to do from here on out every week, I'm going to bring one figure from the history of computer science and hopefully try and show you that the history of computer science is very diverse. There are all different groups of people, some of whose narratives are more accentuated and some narratives that are less accentuated that make up the history of computing. So hopefully you can all see yourselves reflected in the stories that we're going to tell. So, onto another very important computing pioneer. You can see here at the list of very top YouTube influencers, we've got Mr. Beast at number 2, and then number 1, Dr. Connie. Now, you might ask how I arrived at this list. Well, one way I could have done it, this was my algorithm. I took everyone on YouTube, I took their view counts, and then what did I do to find out who were the top influencers? What would I have had to have done? I've got this pile of data, I've got the names of people and how many view counts. What do I have to do to figure out the top 4 people? I have to sort them, so I have to get them in an order such that I can figure out who's the number 1 influencer, me of course, the number 2 influencer, Mr. Beast, and so on and so forth. Now this list is a little old, so I don't really recognize some of these later ones, so maybe one of you, after finishing today's class, can go and repeat this exercise and tell me who today's top 5 influencers are. I will warn you, I still expect to be number 1 in whatever ranking you use. So today what we're going to do is we're going to use a bit more of the techniques that we learned last time about manipulating computers' memory to figure out how to get things into sorted order, and then as well how to go through the different things that we've found and try and find a particular element that we're interested in. This is the problem known as searching. However, before we do that, we're going to need to do a little bit of a recap about how computer memory works in order for us to start to build the data structures, the ways of organizing data that will actually allow us to perform both sorting and searching. So you'll remember from last time, we were starting to deal with computers' memory and the way it was organized. And one of the jobs of the operating system is to tell our program which parts of the computer's memory it's allowed to read and which part it's not. And if our program touches something it's not allowed to read, you probably heard this word last time. Does anyone know what we get? Segfault. So if you write to a place that doesn't exist or a place that you're not allowed, segfault. So modern operating systems do not allow you to address certain places. So for example, the address 0 is reserved for what we call the null pointer. And you saw this last week, and the reason we do this is because otherwise you have no way to tell if a given pointer is going to be valid or invalid. Because if you use every single possible address, including 0, then what do you use for a variable that should be empty, such that you can identify when a pointer isn't filled yet, isn't ready yet? So the operating system, as a result, is going to segfault if you try and dereference a pointer that is set to null. And remember, dereferencing was this idea of actually going to location where the pointer is pointing to. So if our pointer set contains the value 0x10, that's 10 in hexadecimal, equivalent to the number 16. The number 16. Then if we dereference that pointer, it goes to address number 16. And we'll do a little more of a demo on this on the slides again, just to help solidify your memory from last time. So the way that the computer memory is organized, again, this is just a bit of a recap. We have all these different regions, which the operating system sets out to be used for different parts of our program. So as I was just mentioning to Tim right before, one of the key areas that you have been using all throughout this course already without even realizing it is called the stack. Every time you create one of the variables using the techniques that you know already, that variable is added to the stack. And it's just like a stack of pancakes. So the first variable you create is at the bottom of the stack. The next variable is the second from the bottom and goes on top of that one. The third variable is the 3 high. And then when you want to take things off the stack, you can go in reverse order. But we'll learn more about stacks a little bit later. Now, confusingly, in the way we frequently draw the computer's memory, the stack grows downwards. So it's like a kind of an upside down plate where the pancakes stick to the top. It's a kind of a funny picture. Now, another thing that I was asked just earlier this morning was, okay, so where do we store the instructions of the program itself? Because when you write a program and the computer is reading the next thing to do, that's information itself as well. You need to store your program somewhere. You don't just need to store your variables, you need to store the instructions that the computer is going to do next. So that happens in the text region. But if you try and write to the text region, you're going to get a segmentation fault, a seg fault. This means that you're trying to access a segment, one of these blocks, that you don't have permission to access. And why don't we want to allow programs to write to the text region? Why might that be dangerous? Anyone have an idea?
If the text region is where the computer is reading instructions from, it would mean that you could directly write, like within a program, write more instructions to the computer. So you could write, it'd be pretty easy to write malicious instructions to the computer just from any old program.
Exactly. So let's imagine that you're taking in, what is your name? And the user has some clever way of writing in some data that instead of just filling up the name variable, starts writing to the text region. We don't want to allow the user to write data into the text region because then they can gain control of the program. And indeed, for many, many years, the text region was not protected and did not throw a segmentation fault when you tried to write to it, which meant that users could maliciously take control and hack programs. And for a long time, this is what people thought of as hacking. Now, there are still ways to sometimes get around these blocks, but this is one of the key protections that exist in modern operating systems. So, again, revisiting what we learned from last time, one way of thinking about the computer's memory is just as a set of blocks, labeled with their addresses and locations. Now, of course, as I mentioned, we don't really use location 0, so we're going to give these things slightly more realistic addresses. Now, again, we're not all the way to realism yet, because if I wanted to write the full address, it would take more room than I actually have on the screen. So we're going to start here at address 0x8. Now again, I'm in hexadecimal, that's base 16, so I can count 1, 2, 3, 4, 5, 6, 7, 8, 9, and now I run out of symbols if I want to go above 9, so instead of having another digit that's like, I don't know, 9 zzz or something, we use the letter A, then the letter B, then the letter C, then the letter D, then the letter E, then the letter F. We now have 16 symbols. And when you reach the end of your symbol set, so we say we're only going to allow 16 symbols to rotate in each place, then you add a 1 in the next place and a 0 in the old place. So it's just like in decimal, we have 10 symbols. We've got 0 to 9, And once we go from 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, we've run out of symbols in decimal. So we zero the place that we're in, and we add a 1 in the next column. And now we can start going to the ones column again and go from 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Tim?
What does the 0x mean at the start?
0x is just a way to remind ourselves that this isn't a decimal number. It tells us that whatever comes next is going to be in base 16. So it's not actually, the computer's not interpreting that 0x literally, it's just a way for us to remember that the number written next is in base 16. Now in binary, the way that's often written is 0b, just to tell the person reading it that actually this is a binary number. It's not like 10,1011 or whatever it happens to be. So in this example here, we have written 3, 4, 5 characters into our array, into our, I gave the game away almost, into our set of memory locations. Does anyone remember off the top of their head what a capital A is at least in ASCII? 65, so pretty close. So what we can do is we can convert all of these symbols, these letters, into their ASCII values. Let's go here. And so if I were to write this out, because these are lowercase, they're a little bit higher, so we get 104, 101, 108, 108, 1110. Now, is that 0 a null pointer? No. Your name was, again? Yeah. So why isn't it a null pointer? It's just an ASCII code. We're not trying to treat this as an address. We haven't told the computer that the thing that is in location 30 is going to be a pointer. It's just a value. But we do call it a null byte. Now, this can be a bit confusing, the difference between a null pointer and a null byte. But in fact, they're actually even spelt differently. The null for a byte is 1L, and the null for a pointer is 2 Ls. Now, that's really confusing. Another thing you'll notice here is that the addresses that I'm using don't go up by 1 every time. In fact, they're going up by 1 byte each time, 1 byte being 8 bits. Now, the reason why we don't use bits for addressing is really just an artifact of computer history. Very early computers did use bits, but it turns out for the most part, when programmers were writing programs, they didn't actually use bits, because a bit can't contain very much information. The smallest amount of information that people reasonably used was a byte, because this enabled us to store at least the basic ASCII characters, which, remember, early on in history was only 127 different characters. So after we started using bytes very frequently, that kind of stuck around as the most basic unit of addressing, and now computers are architected around it. There are also some efficiency reasons why you might choose a byte, but for that, you'll have to take a microarchitecture class later on. Okay, so now what I'm going to do, I'm just going to flip the orientation of my picture here. It's the same thing as before. We have another question.
I was just curious, if it's bytes and it goes up by 8, then why is it 8 and then 10?
Because we're operating in base 16, unless I've made a mistake.
Base 16?
Yeah. So it's hexadecimal. So after 8, 8, 9, A, B, C, D, E, F, 1, 0.
Oh, my bad.
So I do have that right. So it looks like it's going from 8 to 10, but it's really going from 8 to 16. It's just that we've written 16 in base 16, and in base 16, that's 1, 0. So we can see here, I've just written out the same kind of thing again. I've written out my memory addresses. I've filled them out with certain values. Only now, some of the values I've actually notated in hexadecimal. Now again, inside the computer's memory, there's no difference between something that's written base 16 and something written that's base 10. It's the same configuration of bits that are flipped on or flipped off. The reason I'm notating it here is just for our convenience, to kind of remember what kind of value we might have stored in each location. So it is natural to interpret a variable that we might have stored in a sequence of these locations as an address itself, because after all, addresses are numbers, and also variables can contain numbers. So we can do this kind of dual representation. And it was Grav? No, GAR. Garv, sorry, got close.
So, why has the value that used to be like 104 then changed to OX?
Oh, I just changed what's in the variables.
Oh, okay.
Yeah, so this is a new set of values that I put into memory.
Okay, they're different. Cool.
I probably should correct that up for next year. So in this example, if we are looking at 32 bits at a time, which is the case if we're using a 32-bit computer, a pointer is going to be 32 bits long. So imagine we're using a 32-bit computer and we're looking at the value starting at 8 and going up to 20 in base 16, so 0x20. So we could read that as 00000030 if we read all the bytes as belonging to one variable. And indeed, if we want to store an integer, we're also going to need to do something similar, treating a set of bytes as a single variable. So a standard 32-bit integer is going to be 4 bytes. And because we can store, again, a number and a pointer are kind of the same thing. They're both just numeric value. In this case, we could imagine that our value starting at 0x8 is either a 32-bit integer or a 32-bit pointer. Now, you might have heard when you were growing up that some computers were 32-bit and some were 64-bit, or this phone is 64-bit or 32-bit. Put your hands up if you heard something like that somewhere in your life. So really what that's talking about is the basic unit around which your particular device's chips are designed. So what is really efficient for your device to work with? For earlier devices from like, say, the 80s to the early 2010s, 32-bit was the most common. But we ran into a problem, and Tim and I were again discussing this just before. If you only have 32 bits, that means you're limited to addresses that can be represented in 32 bits. And a 32-bit number, we're going back to week 1, I think it was, we remembered that you can only store a value up to about 4 billion in 32 bits, which means you can only have about 4 billion different addresses, which is equivalent to 4 gigabytes. So if you buy an old 32-bit computer, you can actually only really use 4 gigabytes in it. In fact, Windows XP was limited to around 3 gigabytes or just a bit over. And now there are fancy ways you can get around this. You could say, well, didn't you show us in that example that you could use like 2 clocks and make your numbers bigger? But if you do that, then you're starting to put a lot more computational processing power into doing very basic operations, which slows down your computer a lot. So one thing that we did to resolve this was we actually started designing chips where the word size is 64 bits. And the word is what we use to refer to the basic length around which the chips in your computer are designed. Garv again.
Does that mean that, like, 100 years into the future, we might find a need for, like, 128-bit processors?
So the growth in the size of the number as you add bits is exponential. It goes up by 2 every time. Sorry, it goes up by a factor of 2 every time. So if you add 2 bits, that gives you 4. If you add 3 bits, you multiply the number of addresses by 8, et cetera, et cetera.
Yeah.
So we didn't just add another 4 billion.
Yeah.
We raised it, we multiplied it by 2 to the 32.
Nice.
So that gives us a lot of room for growth. I forget what the actual limit is, but I think it might be someone can calculate it for me, and maybe we'll come back later of how much memory is addressable by 2 to the 64. But it's large enough that I'm at least not thinking about it for the foreseeable future. So you can see that in our picture here, let's go back to it, we could also treat each one of these cells as a single byte. So rather than connecting it up, 4 of them like I did before for a 32-bit integer, I could just say, let's look at one character. Let's look at 8 bits at a time. So in this case, address 0x30, 8 bits together is going to give us the number 10, and I've just written it here in decimal. So depending on what we instruct our C program, we can tell it to treat different chunks of memory as belonging to a group. And this is going to be an idea that we revisit really soon when we get to arrays. So Does someone now want to explain why in C, why we always include a type declaration out the front? Does anyone have an idea? Over here, let's get the microphone. And remind me your name again? Ben.
So when you're calling that variable, it knows what space of memory to look at because different variable types have different data types have different memory segments that are required. So a character would have less than an integer.
Exactly. So
when you have arrays and you're addressing this much belongs to this index, you go then move to the you know how much bytes to look at before you move.
So we haven't gotten up to that, but yes, you are correct. So if we tell the computer that this variable is a char, when it goes to read from the memory slot where the char belongs, it's only going to read 8 bits. If it read more, that would no longer be a char, that would be an integer, for example. And same thing with pointers. When we tell our computer that something is a pointer, it's going to read up to the word size that our computer is designed around. So for example, on my modern laptop, it's going to read 64 bits, which is equivalent to 8 bytes. Remember, to get from bits to bytes, just divide by 8. Okay, so this whole thing works because addresses are numbers and addresses also store numbers. We've got this kind of dual functionality going on. So then how do we know which variable is actually to be treated as a number and which is to be treated as an address? Ben? But how do we know if something's a pointer or something's not a pointer?
Data types?
Yep. And how do we do that in C?
Declaration.
Yeah, so we just have our declaration. So if you remember, we have our declaration when we have a variable that begins with a star that indicates that it is a pointer to that data type. Now this can get confusing. So a pointer to a char, how large, I'd love to have a polling tool set up, but I don't. How large is a pointer to a char? So left hand for 1 byte, right hand for 4 bytes, hands on head for 8 bytes. How large is a pointer to a char? Left hand 1 byte, right hand 4 bytes, hands on head 8 bytes. Okay, let's hear from this guy over here why you said 4 bytes.
Oh, no, I had my left hand up.
Oh,
I said
1 byte.
1 byte, yeah.
Okay.
The reason I said that is because the char itself is just 1 byte, so it should just be equal to that since we've declared it to be a char.
Okay, someone who had their right hand up. Someone who had their right hand up.
We need a microphone which is like a bowl, so you can just like throw it.
That would be good. That'd be a lot of fun.
Because although it is a char and it's only 1 byte, we have a lot of chars, and so we need to specify where in memory it is. So if it's 4 bytes, that gives you a lot more possibilities in terms of specifying where the char is in memory.
Okay, and someone who had hands on heads. Ella, did you have hands on head?
Oh, no, not first line.
Give it a go.
I think it
Oh,
depends on the computer, whether it is 32 or 64-bit. So I think if you have a 64-bit computer, it's going to be 8 bytes.
Yeah, so putting all of that together, it was actually a poorly defined question because I didn't tell you which computer it's on. So if it was on a computer that only had room for 256 things in memory altogether, that was the entire span of its memory, then the answer 1 byte might have been correct. But we know that modern computers aren't designed with just 256 memory addresses. They're designed with at minimum like 4 gigabytes, and most modern computers can have some things like 64 gigabytes, 128 gigabytes. What that means is that the people who said 8 bytes we're essentially saying you need a 64-bit pointer because in the computer that those people were anticipating, you're going to have so many different memory addresses that to point to one specific memory address, you're going to need 64 bits of information. And so everyone who said 32 bits is correct as long as the machine is a 32-bit machine. And even the people who said it's the size of 8 bits or 1 character had a leg to stand on, although you'd have to work very hard to find a machine that has a pointer of that size. Again, just to repeat why, even if the thing we're pointing to is small, the amount of memory we need in order to point to something is going to be larger than that typically. We're going to need at least 32 bits for a 32-bit machine, or 64 bits for a 64-bit machine to actually store the pointer itself. So just like we see in this picture, this is a 32-bit machine. So if we're going to declare char star a, so this is a pointer to a character, the computer is going to set aside 4 bytes on a 32-bit machine, and here's an example address that we're put in there, 00000020, which, if we translate that to a shorter number and lop off the zeros, is going to be 0x20. And then if we look at location 0x20, we can see that's just 1 character in size, because we're only pointing to 1 character. And then star A, if we dereference A, that'll give us the letter D, which is 60. Oh, there's actually a mistake here. Can anyone see the mistake? I've written 0x68. Is that the letter D? It's not the letter D. The letter D is just 68 in decimal. And so I've actually made a mistake here that you can tell. There should be no 0x over there. Okay, so things can get confusing fast, so don't worry if this slide is a little much for you at this point in time. But we can have a pointer that points to another pointer. So you can see here we have a 4-byte pointer that is now pointing to another 4-byte pointer. So as I said before, the star operator is officially known as the dereferencing operator, and for those of you paying attention to the back catalog of lectures, you might have seen the dereferencing dance, which I like to do whenever I dereference a pointer. So remember how C was passed by value? Does anyone have an idea of what happens if we pass a function an address? Again, this is just going back to last lecture. Why might we pass a function an address? What are the benefits of that? Let's get from someone further in the back.
We might pass it an address instead of a value because that way it won't make a copy of the variable and instead actually take the contents of that variable and do whatever it wants to it, so that when we look at the variable again, we'll see that it's actually changing the functions done what it's supposed to do.
Yeah, so if we pass the pointer, what we're actually doing is we're giving a copy of the address to that function, which means that other function, so let's say function A passed an address to function B and A now can talk about the same location in memory, so function B can edit that location, and when we get back to function A later in time, function A will see the changes that function B has done, which is not true if we just gave it the variable itself, because remember, C is passed by value, so we're just giving it a copy. So if we give it the value itself, and function B changes the copy, when you get back to function A, that variable isn't going to have changed. So this also allows us to effectively return multiple things from a function because we can modify things that were in the original function. So what happens if you don't have permission in the second function to access the address that the first function gave you? What does the computer do? Nice and loud? Segfault. We'll see this a couple more times. So we've talked about null pointers. If you dereference a null pointer, what do you get? Come on. Segfault. Just making sure you're all awake. It's a trap. How did I do with my Admiral Akbar? Thumbs up, thumbs down? Thumbs up? Okay, we're doing okay there. Now we're going to see this a few times in semester. There are going to be a number of tricky things that are where certain symbols are reused in multiple ways. So one question that we might hypothetically ask on an upcoming mid-semester is, what are all the different ways that the star symbol could be used in C? So some of the ways in which it's used is as the multiplication operator, as the dereferencing operator, and as part of the type declaration for a variable to indicate that the type of the variable is going to be a pointer. And remember, this is distinct from actually doing the dereference. This is indicating to the computer that, yes, we're on a 64-bit machine, so please set aside 8 bytes because this thing is going to be a pointer. And those two operations are different. Garv.
How does the compiler know the difference between what to do if it's the same symbol? How does the compiler know the difference between what to do for each of the use cases of the symbol?
Unfortunately, we no longer offer a compilers class at Melbourne Uni, but that is what you'd learn in there, is there's a whole complicated, what we call a grammar for a language that identifies if certain symbols appear in different places, how should they be interpreted? And so C has a very strict grammar that says, well, if it appears in this kind of location, the compiler should treat it this way. However, for the purposes of this class, we know if it appears in a declaration, and we know what a declaration looks like just from our experience. It has the type, and then a star if we're going to make it a pointer type, and then the name. If it appears like that, then it is a type the use in the type declaration. If it appears between two variables, then it is going to be a multiplication, and if it appears before a variable name, then it is going to be a multiplication operator, unless that's part of a type declaration. Sorry, then it's going to be a dereferencing operator, unless it's part of a type declaration. So this actually takes a little bit of work to get your head around. Okay, I think we'll only look at one pointer program, and then we will move on to arrays and some of the more exciting stuff for the day. So let's see if... So we are going to start our program with the standard libraries that we're used to already including, so standard IO and standard library.h. Now we are going to write a function and we're just going to create a function prototype for the minute. And our goal here is keep reading in numbers until we find one that's within a certain range, so between low and high. So one thing we might want to do is write a comment until you find. Okay, so let's draft out what this function might look like. And does anyone have an idea why I'm using a pointer here as my third variable? Why might I want to do this? Lottie.
So that after you read a number, you can save it at an address and then access it outside of the function.
Yeah, so what we can actually do is inside our main function, what we can do is call read num, do something like this. And now we know when read num finishes, as long as it's been successful, then value is going to contain the actual value that was read in. But how do we know if it was successful or not, given that we can't use negative numbers to indicate failure here? That's what we're going to use the return value for. So we'll do something like if read num does not equal read OK. Oop. And exit failure. Now there are going to be a few new features here. So the first thing I'm going to do is I'm going to use a hash define for read OK. Now have you seen hash defines thus far in class? Sasha gone over that with you? Great. Ella?
Wait, sorry, I'm still not clear why we're using the the asterisk num in the read.
Okay, I'll go over that again in 1 second.
Thank you.
So the other thing that you may not have seen before is this exit function. Have you seen exit already in class? Okay, you've seen it. And exit failure is a value defined in standard lib.h. And the reason we use that is so the shell that's running our program gets a return value that indicates if the program exited successfully or not. So Ella asks, wait, why are we using this whole pointer mechanism in the first place? Well, what this is illustrating is that it allows us to, if we returned just value from the function, so if at the end of read num, I returned the value I found, we don't know whether the function was successful or not. Instead, all we have is that number that it gave us at the end. But what if the function was unsuccessful? Well, we want a way to be able to give back to the main program two things, both the number we found and whether it was successful or not. And because C allows us to only return one thing, we're using a workaround here. The return value from the function is going to be success or failure, but what the pointer is going to allow us to do is it's going to allow us to actually change something in that main function, and the thing we're going to change is the value that we found. And so we know if it returns successful, then that location in memory inside the main function is now going to contain the correct value that was read in. Garv.
Can we imagine that process sort of like creating like global variables in Python?
No.
That's completely different?
No, completely different, because global variables in Python are visible to any part of the program. It means essentially that any function can look up the address of that variable and access it.
Yeah.
Whereas with pointers, you can very carefully control who knows that address and therefore who can access it.
And that's what we were talking about with the permission stuff before.
A little bit. We can't go too much into it now. Feel free to chat to me after, but generally that's some of the idea there.
Nice.
And when we talk about dynamic memory allocation later in semester, it'll become even more clear how that all starts to play together. Tim.
So I think, correct me if I'm wrong, but I think the similarity you might have been getting at in terms of global variables in Python is, although it's completely different, it is similar insofar as if you have a
local variable inside a function in C, when you change the value and then you go and like, it won't affect anything else anywhere in the program. But because you're referencing it by the pointer, you can therefore go and edit things that actually are out of scope.
Yes.
Yeah.
So in that way they are similar. It allows you to access something that is, in theory, in a different scope. But the way that pointers and scope work is a little complicated. So if, for normal variables, so for, let's say, this value variable, it only exists as long as the main function is still running. Now, the main function being the main function, that's less interesting, so let's do it with another variable. Let's have the status variable there. The status variable here only exists so long as read num is still running. Even if you used a pointer to it and put the pointer somewhere else, if the read num function is finished running, that variable doesn't exist anymore. The address still exists, because it's somewhere in the computer's memory, but it's not valid anymore. And so this is where global variables tend to be very different, because global variables are going to exist regardless of what particular function is running at a given time. The similarity being, though, that both of them give you ways of accessing state that belongs to a different part of the program.
So you said that, like, with in this case, the variable status, obviously it's only seen in the function scope, and so once the function finishes, we won't be able to see it.
Yeah.
The address will still exist. Does that mean if, say, hypothetically, we knew the exact address that variable was created in, we could still access the contents, or do they also get, like...
So what happens is the C language says once a program goes out of scope and is destroyed, you get no guarantees whatsoever about what's going on at that address. So that address might be reused by a different part of the program for a different variable. Your operating system might decide that it wants that bit of memory and do something with it. So essentially you get into territory that's called undefined behavior, which means that the computer can do anything at that point. And so that is why it's dangerous, even if you know the address of a particular location in memory. If the language specification does not allow you to use that location for a variable, you can run into serious trouble. And we had another question, no, we're good? Okay, so let's write a bit more of our program here. So I have read OK, and I'm going to also define read error, just to keep my program clean. So we know if we reach this point that the value has successfully been read in. And now notice here that I haven't actually created a pointer. I've just created a normal variable. But by getting the address of that normal variable here, I'm able to give the other function something that looks to that other function like a pointer. So if I take a normal variable and I get the address of that variable, that essentially creates a pointer from that variable's location, so where that variable exists. So let's say that the compiler has decided that, and the operating system have decided that my variable value is going to be located at location 0x50. When I use the ampersand, that is going to take the value 0x50 and copy it into the readNum function. And because I've copied in an address, the readNum function realizes that over here what it's receiving is in actual effect a pointer to a number, even though I haven't declared it explicitly as such in here. Another way to write it, if I wanted to make it a bit clearer, could be something like this. So I've just declared a pointer to an integer, and now that might read a little more clearly to all of you, even though they're doing the exact same thing. Tim?
So you want to get rid of the ampersand in that case, right?
Oh, yes, should have deleted the ampersand there. Same effect as what I had there before. Okay, so now what I'm going to do, I'm going to just write this up quickly because we've seen and low, high. I have made another mistake there. Live coding is hard, guys. Okay. So what I've done here is I've used scanf to just read in a number into next. And now you'll notice something that you might not have paid attention to before. Scanf is also using pointers. See, what I'm doing over here is I'm giving it the address of the next variable. And so this is why when we use scanf, we include the ampersands, because we want it to actually read in something from the user and modify the variable in the function that was calling scanf. So this explains a mystery we've had the whole time up until now. So now we just want to do the check to see if the number is in the right range. So this means we've successfully read it in. And then if for some reason the user has stopped entering numbers, they've hit Control D, and we haven't already hit a number in the right range, return read error. And there our program is complete. So let's go into FOA lecture 4, and I'm going to use Clang. And hopefully I have not done any errors. So give us a number between negative 100 and 100, so negative 250. Nope, doesn't do anything. 123 doesn't do anything. Now let's try 70. Value equals 70. Now you'll notice I didn't do a good job of adding in new line characters here to make the output nice. You can do that on your own time. And there is an example of where we might use pointers and as well why we might use them. But we still want to go back to our thing at the beginning of class, which if you remember, we wanted to figure out who is the most influency of all the influences. We're still not quite there, but I think we've had a big chunk so far, so we're going to take a 5-minute break and resume at 10:57, and then we'll start to get the next piece of the puzzle we need before finally getting to the top influencer. Okay, see you all in 5. And we are back, everyone, and back to our tabula rasa, which is Latin for empty slate, representing our blank computer memory here. Now, so far, we've been treating each cell typically as its own individual unit, or sometimes we've been saying, well, maybe we can group 4 of them together to be an integer, or 8 of them together to be a pointer. But what happens if we want to actually still treat them as individual cells, but start to think of them in groups? So each one can contain a number, but maybe we want to think about 6 numbers at once. Why would we want to do this? Anyone have an idea? Why do I care about grouping things that way, where I have 6 individual numbers rather than 6 cells that make up one number? Ethan?
If they're related somehow, you might want to do operations on them at the same time or one after.
Why on earth would you have a collection of related numbers?
No idea. That seems like a very unrealistic situation.
Where in your life do you think there are collections of related numbers?
Maybe, for instance, timetable at uni. I've got my first class, when that starts, then when my next one starts.
Okay, what's the first thing you do when deciding what clothes to wear on a given day?
I'll check the temperature.
Check the temperature. So we might have, what might we have in each of these 6 slots?
You could have the temperature on Monday or Tuesday.
Yeah, so these numbers are related to each other. They shouldn't all be in the same box. We shouldn't combine the boxes to make it like a 32-bit integer out of the temperature on every day. But we still want to be able to connect these different numbers together. Or in the case of what we're discussing, view counts for YouTube influencers. So we might want to have one box represents the view count of each influencer, or if we're being really sophisticated, we might want to find a way to have each box represent both the name of the influencer and their view count. But that is going to take a little more sophistication that we might not get to later today. So this collection of like objects, where there is the same type of thing in every box, but there are multiple of them, is known as an array. And an array is our very first and very most basic data structure. So we can fill up boxes with different values, as we just discussed. And the reason we want to do this is because most of the data in the world doesn't just come in 1s and 2s. Most data comes in very large sets. So whether that's organized by times or by days or by different entities, and by different entities I mean like we have one piece of information for every student in the class. For example, if I'm keeping a list of your grades, or we have many seats on a plane that we might want to have information about every passenger. But essentially for every one of those units, the data that we want to store is the same. So it might be a unit of passenger information or a unit of temperature information. But an array allows us to store sequential values of let me say that again. An array allows us to store a linear collection of objects that are the same. Now, in some other programming languages, arrays are a little less well defined, and at least syntactically in the language, you can store different types of things in what looks like an array. But at least for the purposes of analysis, for the purpose of formal computer science, and indeed for the purposes of programming in C, we're going to require that all the objects in the array are of the same data type. So either they're all integers, they're all chars, they're all doubles, they're all floats. So an array is a data type. You can declare it in a variable declaration, but it's also a data structure. It represents a way of arranging information, and in this case, the way of arranging the information is just linearly, one block of information after the next. An array might also seem like a bit of a boring data structure, but my job in the next part of lecture is to convince you that really they're not so boring. There's a lot of interesting things you can do with them, and a lot of interesting algorithmic properties that are used by arrays. Now, this is the real kicker, and the reason we just spent another whole 50 minutes on pointers is that arrays and pointers in C are essentially at the lowest level really the same thing. Arrays in C are just pointers with different syntax. And we can kind of see why. Because a pointer allows us to reference a location in memory, and locations in memory occur sequentially. So just like we had address 0x8 was followed by address 0x10, well, those are the same chunk sizes of information arranged linearly in memory. So pointers and arrays really are doing the same kind of work. And so what we call this ability to do the same thing in two different ways that's essentially treated by the compiler as identical, we call that syntactic sugar. It's a sweet way of doing the same thing using a slightly different syntax. And the reason we might do this is because pointer syntax, as you've all seen from last week and the start of this week, can be a bit confusing. Remembering when do I use the ampersand, when do I use the star, what's going on with this pointer to pointer thing. The syntax that's used for arrays is a little simpler. So as long as you're not trying to do anything too fancy with the pointers, the array syntax unlocks a lot of the same capabilities without some of the headaches. So we have a few different options in C for creating an array, and we will go over a little bit of the boring syntax, but I should let you know from this point on, I'm going to be expecting you to pick up more of the syntax on your own. We're not going to spend as long on the syntactic details in class. So one thing we can do for creating an array is just let the computer know that we want to save the memory for the array and to set it out for us ahead of time. We're not going to fill it up with anything. Just like you can create an integer and not set the value of an integer, we can do the same thing with an array. So this first line here, char A6, says set aside room for 6 characters sequentially on the stack. And when I say the stack, as I mentioned earlier today, that's just the place where all the main variables that we've been allocating for our program live. We could also both allocate the memory for the array, so we could tell the compiler to set aside that memory, but also initialize it. This means filling it up. And so in this case, I'm going to fill up my character array with the following characters, HELLO, and then a null byte. Remember, that's null with 1 L in this case. And teaser, this is really going to be what we'll call soon a string. But stay tuned for next week, I think, when we will get to that. We could also create a pointer to the start of the array. So here we have a char star, which is a pointer to a character. How many bytes does that take up on a normal computer that we'd use today? 8. You got it right this time. What was your name again? Aaron. Yeah, so Aaron tells us this is going to take up 8 bytes. And how many bytes is our array going to be in this case? Not quite. How large is a character? 1, yep. And we wanted room for 6 of them. So we have now taken up 6 bytes for our character array. And the pointer is 8 bytes, because all we need for the pointer is to point to the very start, to the very first one. And then we know there are 6 of them, and we know that they're spaced evenly. So we can jump between the different characters in the array just by saying, OK, let's go to the pointer's address plus 1, because that'll take us to the next character. Let's get you the microphone. Aaron.
I was going to say, if the pointer is such a simple thing which is close to the machine operation, why does it take up so much memory compared to a character?
The reason that we want our pointers to be big is so that they can fit all the different possible memory addresses, so they can point to anywhere inside the computer's memory.
Okay, so the larger it is, basically, the more we can create, and then the more things we can point to in memory.
Yeah, so if I tell you that your pointer can only have 256 values, that means your computer could only have 256 locations that you could point to.
Okay.
And that's a pretty sad computer. So by making our pointers bigger, that enables us to have more memory inside the computer and ultimately allows us to store and deal with more data.
All right.
So now if I said, OK, let's have a character array of 32,000 characters, the pointer would still only be 8 bytes, even though the array would be 32,000 bytes. Just a warning, if you try and allocate an array of 32,000 bytes on your machine, you might get an error. We'll have a little more discussion around how to deal with very large arrays later on in semester. So I would honestly encourage you to experiment. See what is the smallest array you can create, what is the largest array you can create, and what happens when you do operations on those. So one thing you'll notice here in this syntax is I didn't have to use the ampersand operator in this syntax to get my character pointer to point to the start of the array. Darcy, do you have an idea why that might be?
Basically because an array is just a pointer to the first character.
Yeah, so what's going on here? When I created the array, remember it's this whole syntactic sugar idea. What I'm really doing is I'm saying create a pointer to a location in memory and set aside the six subsequent locations to be valid for use. And remember, the reason why we have to say that they're valid for use is because otherwise the computer might use those locations for something different. So what this syntax char A6 means is give me a pointer to the first one of these locations, but make sure that there are 6 locations total set aside for values that I want to store, each of size 1 byte. Let's pass the microphone back because we've got a couple folks with questions.
How does the computer choose which addresses to use? Like when you set that array, how does it decide which address it's going to start at?
But all variables that you create normally are inside this region of memory called the stack. And remember, it's this like kind of upside down pancake thing going on. So the first address will be taken up by the first variable that you create. The next variable that you create will take the next lowest address, and so on and so forth. You can actually see that the addresses are starting at the highest address, which is 0xFFFFFF, and going down to 0. So every time you create a variable, the compiler is going to pick the next location down from that.
Right. Thank you.
The only caveat is remember that when a function ends, a whole lot of variables are destroyed. So what is actually going to be happening is this stack is going to be getting larger and smaller and larger and smaller. And so for each function, you may actually end up reusing the same address because it would be an address that was from something that used to sit in that location but was part of an old function that's no longer there.
So I was just asking, because in your example where you created the array and initialized it, you had, I think, the null byte or null character at the very end.
Yeah, let me go to where that is.
So it was like the 0 with the backwards
Yeah.
/
I put a null byte at the end.
So is that just like another character in the 256 potential characters? Is that something slightly different?
So it is one of the normal ASCII characters. It's the character that's also represented by the number 0 as well as this \0. So in ASCII, a computer that is well behaved will always convert that /0 into the number 0. But even if you have a computer that is poorly behaved and decides that all the ASCII values are going to be different, this will still represent the null. And we'll talk about why we use that next week when we talk about strings. And it was Danny, right?
So where you've got the 6 there, can that be a variable?
Where I've got, it can be a variable. So you can determine how large you need an array to be based on some computation that you've done. So you can say, please enter how many numbers you wish to enter, and the user types in 50. And then you create an array for 50 characters, and you say now, please enter your numbers, and then you can store them sequentially in those slots. So that's our array creation. And, forgotten your name already. Alex. Alex, behind your Alex as well. All the Alexes, put your hands up. Okay, only 3 today. We're doing all right.
Sorry, I just had a question regarding the stack. You mentioned how once a function stops running, it kind of destroys the variables, right? And the size of the stack kind of shrinks. Does that mean the memory address for the existing variables within that stack shift to display?
No, so the stack shrinks because a bunch of variables were all the variables for that function were destroyed, but all the variables that are still being used are not part of that, weren't part of that function, so they've still stayed the same.
Yeah, so when you assign a new variable, does it build on from there, or does it displace the first?
It builds on from the top of the stack.
Okay.
Which in our case is the bottom because our stack is upside down.
Yeah, okay. Yeah, makes sense. All right, thank you.
Okay, so in the case of, as Darcy mentioned a second before, A is just a disguised pointer. When we're talking about our array variable is just a disguised pointer pointing to the start of the memory that we've created. So in this case, we've asked the computer to allocate 6 locations for characters and return the address of the first location and put it in the variable A. So then we can write something like this: the ith element of array A. So if you want to access the 0th element, which is, remember, the first one in computer speak, we can write A0. And if we want to access the last element in an array of 6 items, what number would I substitute in for I? Just say it out loud. How many fingers? Put your fingers up. Fingers? Come on, everyone. Fingers. Gabriel says 2. Not sure why. 6. Okay, the correct answer is 5, because if we want to fit 6 items in, we have location 0, location 1, location 2, location 3, location 4, location 5. So 6 items, but it only goes up to number 5. And it was Aaron.
Is it like Python where you can index from the back with a -1?
No, it is not like Python. Doing -1, it might, I don't actually know what it will do. I think it might give you a syntax error. We can try, but if it didn't give you a syntax error, in my mind, the most logical thing for it to do would be to take the value of the pointer and go one backwards into something that's invalid. So given that that's my reasoning, I would expect the compiler to say no. There is no backward indexing, there is no reverse indexing in strings, and that is also partially because in Python arrays are not strictly arrays in the technical term. They're not linear collections of like objects with no extra information added. Python arrays have all this different information associated with them to allow you to do fancy things. You'll notice in the C arrays, there's actually no indication of where the array ends. In the case of my hello here, to indicate where my array ends, I've just put a number 0 in there. To tell me, okay, when I hit the 0, I know that there's no other value that I care about that's going to be 0, so that'll be the end of my array. And so that's what I've done here. But otherwise, you just need to remember how large you made your array. So if you declared your array as having 6 items, well, you'd better store that number 6 somewhere. Otherwise, you won't know where the end is. And that is why, Aaron, why we can't just use the -1, because C doesn't know how large the array is. It doesn't know where the end is. You might have kept track of that in your own variable, but that's not automatically done by the programming language itself. And that's partially done to make arrays and pointers more flexible. Well, we can have a deeper discussion on that outside of class if you're interested, or in the more comfortable tutorials. So this might leave you with the question of what gets passed if you pass an array to a function. So do we have an answer to that? What gets passed if you pass an array to a function? All right, let's give it to someone further back.
The first entry of the array?
Yeah, so we're copying the address of the first location in the array. But because the compiler wants to be nice to us, there actually is syntax that we can use such that we can still, even though we're passing a pointer, there is syntax that we can use such that we can still treat it as an array. However, the C compiler is only so smart, so if you start doing things that are too fancy, and we'll see those a little later in today's class, it will forget that you're actually referring to an array, and the array syntax will stop working. Unfortunately, functions cannot return arrays, but functions can return what else would be useful that might allow us to do something similar-ish? Gabriel?
Yeah, the address of the first location of the array.
It can, but here's a bit of a puzzle for you, and you're a good person to ask. Let's say I'm going to switch over to my other screen here. And no, that is not what I want. And now I'm going to create a function that returns a char star And I'm going to call this bar. And let's ignore the fact that I'm not using a main function here. This is just a little C snippet for the point of our little puzzle. And now I'm going to create an array of 6 characters and return A. What is the big problem here, Gabriel? What happens when, let's chart what happens with our variables and running the program. So let's imagine inside the main function, we call foo, and then let's say just going to try and print out the first character in that array. What's going to go wrong, Gabriel? Anyone else have an idea? Okay. Ankit, you've spoken a lot, and so have you, Gaurav. Someone else. Okay, maybe we'll let Danny give this one a try. Danny's at the end there. Come on, if I can remember all your names, you can definitely do it too.
When you create the array, it returns a pointer to the array, but when the function ends, the array gets destroyed.
Exactly. So inside bar, we have told the computer, create a variable that has room for 6 characters, and at the end, return the address, copy the address of the location you created, and give that address to whatever called you, which in this case was foo. But we know that bar created room at the bottom of the stack, or at the top of the stack, for our 6 characters, and when the function ends, the location of the top of the stack changes, and those 6 characters are now in garbage land. And so while that address still exists, we no longer really have permission to use those variables. So even though foo has the correct location, it has the correct location where those variables were, those variables can now be used by other things. And so we should no longer be touching that memory and no longer have any guarantees about what is there. So what we'd probably need to do is inside of foo, we'd need to do something like this. Then we could do and then we can return the address back and it'll be valid, because now foo is actually the part of the program that has created and allocated memory for those 6 characters. And now we can pass that address around, and until foo ends, that location is going to be valid. Now the other thing what I mentioned we can do is we don't have to pass it as a pointer. We can pass it as an array using this sort of syntax. And now we could do something like A0 equals 1, A1 equals 2, A2 equals 15, etc. And now when we get back to foo, those values are going to have been retained. We're going to do essentially a very similar thing. Actually, let's start with include main. And I'm just using void for convenience. We remember that it should be int argc and char star argv, and we'll talk more about those soon. So I'm creating 2 variables here. What is this variable? Someone shout out. What am I creating there? An array of what? Integers. How many? And 5, yeah. So that's an array of 5 integers and an uninitialized counter variable that I'm just calling I. So now for I equals 0, I is less than n, I plus plus. And I'm just going to calculate values in the geometric sequence. There's no particular special meaning to these numbers other than they form a well-known mathematical sequence. But I'm going to put each of them in successive locations within the array. So the first number is going to be put in location 0. Then when I hits 1, the next number is going to be put in location 1, 2, 3, 4. Will there be a number put in location 5? No, because location referenced by the number 5 is past the end of array because we were using location 0. So remember that one of the biggest errors I see in student code and also in professional people's code are these off by 1 errors where you've forgotten that, oh, it's an array of 5 things, but because it starts at 0, the indices only go from 0 to 4. And now what we're going to do, we're just going to print these out again. And this is a very, very common pattern that you will use in your projects, that you will use in your programming careers. Oh. So all I'm doing here is I'm computing the first 5 values in the geometric sequence. This geometric or arithmetic? Forgotten which one's which. First 5 values in the sequence, filling the array with them, and then printing them out. So let's give this a try, and this is still called test.c. Oh, this is called test.c now. So let's compile it, clang test.c-o test. And we can see 0, the 0th location has number 0, first location has 1, 3, 6, 10. We have just filled an array. Now, it seems very simple. It is very simple, but it's also quite easy to get things wrong because now you're starting to deal with multiple memory locations at once, and so it starts to become easier to make mistakes. So just keep an eye out. So that is really all that I'm going to give you on one-dimensional arrays. From there on, you're now able to use this syntax to store like data of any type within an array. But we are going to turn to Ankit for another question.
I was just gonna ask, because like with the print statement there where you reference the specific index in the array, does it like already, because technically isn't that a pointer, so does it like already dereference?
Yeah, so that's the beautiful thing about using arrays is the dereferencing is automatic. You don't need to think about pointers when you're using the array syntax, which is really very nice. Other questions about this demo? Okay, so now we are ready to move on one more level of complexity, and then finally we will get to our influencer demo. So, two-dimensional arrays. So just like you might want to organize your data in a single row, much data that we have in the world actually comes in 2 dimensions. Who can give me an example of data that might be in 2 dimensions? That's not a real world example. That is a mathematical example of something that might be in 2 dimensions, but yes? Tim?
Maybe if you have temperature data for different cities.
Yeah, so you could have cities 0 to 10, and days of the week, days of the month 0 to 30, and then you would have a matrix of information that way. So there are all different types of information that are represented. I want one more example of something that might be 2-dimensional. It was Alex.
Maybe like tracking students in their grades.
Tracking students in their grades could be a 2-dimensional array. Who said that? And your name was? Honey. Sorry, it's been a couple weeks. What did you say?
Oh, I said a chessboard.
Chessboard, exactly. That's a great example. So there we might have values for every piece, ranging from like, how many different types of pieces are there in chess? 6 types of pieces. So we might have values ranging from 0 to from 0 to 6. And why am I doing 0 to 6 for a chessboard instead of 5?
Be empty.
Yeah, we need something to represent an empty space, and then we could have every location represented by a cell in our matrix. So 2-dimensional arrays in C are really just 1-dimensional arrays that are made a bit longer so that when one row ends, when one row ends, you start with the same row just for the next column, and we know that 1-dimensional arrays are really just pointers. So you can swap out the syntax for a 2-dimensional array for the syntax for a 1-dimensional array in most cases, and you can swap out the 1-dimensional array syntax into pointer syntax. So let's go back here for a minute, and I'm going to make a slight modification to this. And now instead of using the array syntax, which was nice and convenient, I'm actually going to use the pointer syntax because I know that A is really a pointer. Now, if I just compile and run this, I have a problem. What have I forgotten? Ankit was asking me about this 1 minute ago. And it was, wasn't Ben, was it? Sam. 3-letter name.
Was it the, I can't remember whether it would be an ampersand or whether it would be an asterisk, but I think it's one of the two, right?
So what does the ampersand do?
It gets the value?
Ampersand gets the address of something.
Okay, ampersand gets the...
So what does the star do?
The star delimits.
Dereferences.
References.
Dereferences, that's right. So we have an address, and instead of an address, what we want is what is at that address. So we're going to use the star. Now, will this work?
I don't think so, because wouldn't that get the what's at A and then just add
Exactly.
value?
So what should I do?
Add brackets maybe around...
Exactly. So what I want is I want to go to location A, increment where I am from location A. So I want to take another step forward from location A, or maybe I want to take 2 steps forward from location A, and then return what's at that location. So now if I compile it again, I get the same results that I did before. Whereas, if I did this, let's just run it to see what happens. It'll still compile because it is valid code, but now what I'm going to get is I'm going to get that number 0 that it's retrieved. It's retrieving something from that same location every time, but it's just adding 1 to it, and now adding 2 to it, and now adding 3 to it. And that's not what we wanted to do. What we wanted to do was go to location, take the right number of steps forward, collect what is at the location, and then report it back. And that's why we needed the brackets. So a big warning I'm going to give you about it's a trap with arrays and pointers is that C is not going to check to make sure that you haven't taken too many steps such that you're now outside the array, or out too many steps past the pointer such that you have validly allocated it. Let's take the question.
So then would like A of like -1 go to the I equals 0 value, and then A of -2 would go to the n value of 5 that we had before?
So tell me what you want me to try.
I want you to try printf of like A of like -2 in the array. Or like, oh yeah, the pointer -2 kind of thing.
Like that? Is that what you want me to try?
Yeah, but like subbing in the value of A -2 into the string.
Tell me what characters to type.
Let me see. Like printf A hard bracket %d. Yeah, close that equals to %d.
Sure.
And then like -2 for that, and then comma A of -2.
I think this will just give us a compiler error. Yeah. -2 is before the beginning of the array.
Oh, okay, so over there did test the bounds.
So the compiler will sometimes check if you have a negative number, but if you've gone beyond the positive end, it probably won't pick that up. A very, very modern compiler might. Let's give it a try. But in general, this is not guaranteed behavior of the compiler. This is, if your compiler wants to, it can give you some nice error messages, but it's not required to by the C standard.
Okay.
Oh yeah, array index 6 is past the end of the array. That is pretty magical. The first time I taught this class 5 years ago, the compilers did not do that. So it is not a requirement that the compiler does that, at least as far as I'm aware, as of the latest C specification, which is C23. Okay, and as we heard, this kind of behavior can allow someone to maliciously take control of a program if you're taking in user input about what element within the array you should access, and then you don't check that you're within the bounds of the array. So if you prompt the user for which element of the array would you like, and the user asks for element 200, and your array is only 5 elements long, well, now you're just giving the user something that is outside the bounds of the array and might be another variable or might be some random part of the computer's memory. So that can be very dangerous. And if any of you have heard of the heartbleed bug, the bug was similar to this, where the program was reading memory that it shouldn't have and displaying it back to the user. And one way we can think of this is as four different sets of length 2 character arrays. So in this way, we have a grouping that corresponds to our syntax here. So what we're going to have is 4 groupings of character arrays of length 2. But this is not C syntax. You cannot type this in an initialization and expect this to work. This is just me helping you to visualize it. So if we have the elements in our 2-dimensional array, we could imagine each of these individual elements ranging from A to H. That's just how I'm labeling the indices. But this is really the same as just putting all the elements in one long row. C does not really care because your computer is not arranged in a 2-dimensional fashion really explicitly. The way the memory abstraction that we use, the way that the computer thinks of your memory, is of just a long line of values. So in this case, we have values A to H, all of which should be the same type, so in the same length of memory slot in a contiguous fashion. And then if I were to actually try and display it, we could display it as such. So we have 4 groups of 2, and you could orient the array either way, like you could flip it in your head, it doesn't really matter, but this is probably the most natural way to have 4 groups of 4 rows and 2 columns. And we have a question back there.
I had a question. What if we try to, reference outside of the array? Because we have 2 of them, right? So what would happen?
So,
like, what if we put like a 5-2 or maybe like a 4-3? I'm not quite sure if there's any difference.
Yes, so you can run the calculation that we'll do that in a second, but you're doing the same thing as if you were just going outside the bounds of a 1-dimensional array. Only if you think that for each of the first index, it's jumping 2 along. So if you say, if that position in the top leftmost corner is 0, 0, and the one below it is, so 0, 0 is the one in the top left-hand corner, and then if 1, 1 is 1 row down and 1 across, then if we exceed that and say do 5, 1, that would take us not just 1 space beyond the end of the array, but 2 spaces beyond the end of the array. And you can use like basic maths to figure out like where you'll end up in the array based on either a single index or based on your 2 indices. One other, it's a trap about 2-dimensional arrays is that if you have a pointer to a pointer, that is not going to be treated by the compiler as the same as a 2D array, even though you can imagine it's got the same kind of dimensionality going on. And part of the reason why is because, well, the full reason why is that a pointer to a pointer takes you 2 jumps, which is like saying the thing I'm pointing to is an address and then go from there to another address. But really a 2-dimensional array is the same as 1 pointer. It's just a pointer to the start of a longer set of elements that might be pointed to by a 1-dimensional array. Any more questions for the minute? And it was Alex again. Does my head in.
What was I going to ask? So if for that previous example, a square bracket 4-2, is it compiled any differently than A8?
Generally not, but the difference is if you are, let me think. Actually, I'm not sure what if the compiler will ever treat it differently. I don't think it will. The difference it makes, though, is it allows you to use that syntax in other places. So if you've declared it as a 2-dimensional array higher up, then the compiler, when it hits another place where you've used it in a 2-dimensional array, will be able to interpret that.
Okay. Yeah.
But as to whether the actual generated assembly code will ever be different, that you'll have to try out.
Okay. Thank you.
Other questions? We're almost ready for the fun bit. Okay, so let's look at 2D array.c quickly, and then we've got some of the props for today. So here I have one possible declaration of a 2D array, and I'm going to comment out all of these because some of this is invalid code, and we're going to just go through and run some of the examples. There we go. So this is my first version of creating a 2D array. So clang 2D arrays.c arrays. Okay, so that one works fine. I'm able to declare a 2D array using a syntax where I leave one of the indices blank, but where I've initialized all the elements, and so the compiler can automatically infer that this is a 2-2 array. So now I can do something like printf %d a 1 1. And let's add a new line there just for clarity. Keep making that mistake. And then we can see I got the element 4, because remember we're 0 indexed, and so 1 1 is the final element in that array. Okay, now let's create another array B, 2 2, and let's use this syntax. Let's see if this works. So both of these are also valid. So I can declare an array but not initialize it as long as I've given both dimensions. And then I can also declare both dimensions and write it out using this kind of more intuitive syntax where I'm kind of specifying it row by row instead of all at once. So there is a whole lot of fancy syntactic sugar that you can do here. Okay, now let's look at a function that uses a pointer to a pointer. And let's see if it works. It gives us the error just as we expect, because we explained that pointers to pointers do not decay to arrays. So that is a good thing that that errored out. I'm going to comment that back out for us. And now we're actually going to use our, is this in the wrong order? There. So now I'm going to use another syntax to access all the elements in the array. So let's add a /n at the end of this. Make that clearer. Oh, thanks. Always good if someone catches my errors before I do. And we see 1, 2, 3, 4, which is the first 4 elements. But now if we look at the way that I've actually accessed the elements, this is kind of interesting. So I know that the array has 4 elements total, and I shouldn't just be using magic numbers here, but I am because this is a short demo. And what I'm actually doing is I'm using a little bit of mathematical trickery to figure out, okay, if I know there are 4 elements total, and I know the dimensions of the rows and the columns, 2 and 2, then I can compute which row I'm up to and which column I'm up to based on the number of the total number of the element that I'm up to. So if I'm at element number 3, the third element, so let's look at this version of it. The third element is 1, 2, 3. That's going to be at column 0, row 1. And we can do that by cleverly mixing the truncated division operator with the modulo operator. And you can spend a little more time puzzling that out on your own. And then, of course, we can use this syntax to access the contents of the 2D array, where I'm just using the 2D array syntax directly. So our big finding from this is that n-dimensional arrays are really arrays of arrays, including when passed into a function. Now, I'm not going to detail the specific syntax tricks that happen when you pass arrays into a function. For that, please see the textbook or experiment yourself to find it out. One last thing we want to do before we move on to our demo is thinking about adding our own types in C. Now, why might we want to add our own type? What kind of type could we possibly hope to add? And it was Sam. No? Ben. Where's Sam? Sam's there. Ben's here.
Well, like if you had, I guess you want to return to object-oriented programming and you have a thing that needs to have multiple properties. So
Such as?
let's say I'm defining a driver and I need their name, I need their license number, their rego number.
Yeah, so very often data comes combined with a bunch of different features. So instead of having a two-dimensional matrix of students and grades, we could imagine having a one-dimensional array of students, and then each student has a name, has a grade, has classes that they're enrolled in, etc. So we probably want some way in C to add our own types, particularly as we start to get pointers to pointers to pointers to pointers and things. So for now, I'm just going to give you syntax to create your own basic type before we get to compound types, which in C are called structs. But for now, let's just look at this syntax to convert something like that example is bad. Here we go. To convert a more complex type, such as a vector or a square matrix, into something that we can more easily deal with. So here, what we want to do is we say we've got an array of doubles. And what we actually want to do is we want to, instead of always having to refer to an array of doubles as the type, we just want to call it a vector. That's pretty common in maths. Instead of always talking about arrays or one-dimensional matrices of numbers, you just say a vector. And so in C, by using this typedef keyword, we can now, anytime we want to refer to a one-dimensional array of doubles, we can just use the word vector underscore t. We have now defined that type. So over here, I can create a vector t, a, and this is really the same thing as an array of size 5 of doubles, but I just didn't need to write that syntax. Now, one common norm in C, one convention, is that whenever you create a new type, you use the syntax for the name underscore t at the end, just to remind yourself and to remind other programs that this is really one of these custom types that you've created. Another custom type that we might create is a square matrix. And so a square matrix is really just an array of vectors. And so you can see that what we've done here is we've said an array of size 5 of vectors we will call a square matrix. So that's a 5 by 5 array of vectors. Now obviously this only has limited usefulness because we haven't figured out how to include multiple pieces of information about the same thing yet, but we have at least figured out a way to start simplifying some of our types. So we're going to skip this demo. You can look at it on your own time, but you can see how we can easily define matrix addition and vector addition with the help of our new types. So I think now we will give you another 5-minute break, taking us to 11:56, and then we will bust out the props. Okay, everyone, welcome back. We're at the exciting part of today's lecture. I need one super volunteer. This person will get Skittles. And let's just get everyone's names so that I learn a few more.
My name is Bowie.
Bowie?
Yes.
I'm Ronald.
Ronald.
I'm Fosco.
Fosco. Cool name.
I'm Catherine.
Catherine.
I'm Ming.
Ming.
I'm Honey.
Honey. And?
I'm Ed.
Ed. Okay. So it was Honey who is going to have the big brain. Actually, pick an assistant from the audience. You need an assistant.
I can assist.
Okay. Sasha will assist. You've got the big brain.
I have to wear it?
Yes, you have to wear it, but it is very hard to wear in its current state. So you're going to have an assistant who will help you hold it up. And now, everyone else.
It's not stuck on to hold it.
It's not stuck on anymore.
Where's
That was a TBD.
I will hold it.
Okay, it was Ming? Yes. Okay, take a card. Pick a card, any card. And Kathleen?
Catherine.
Catherine. So Honey, We are going to play a sorting game. So your job is going to be, these are like my view counts for all the different influences, and we are going to turn them around.
I can't see them.
Nope, you can't see them. Everyone turn your cards around. You don't have to turn around. Just turn your cards around. Hold them out in front of you, but turn them around. Right? Okay, now hopefully you haven't memorized them. Shuffle yourselves. Just shuffle, random shuffle. Come on, brisk, brisk. Okay, and now the rule is we are going to act just like a computer, and your goal is going to be to get them in sorted order. Let's say highest value over here, smallest value over there. But just like in C programming, you can only compare two things at once. So at any given time, you can only have two cards face forward. And also the only thing you're going to be allowed to do, because this is what we've learned how to do in the class in C, is swap. So the two things you're allowed to do, you're allowed to turn over a card, turn over another card and compare them, and you're allowed to decide whether to swap them or not to swap them.
Okay.
Okay, so the floor is yours, and describe to us what you're doing.
Okay, I'm gonna look at these two cards first. Okay, I'm gonna swap.
And let's say ace low, that's fair.
Sorry?
Let's say ace low instead of ace high.
Yeah, that is why.
Okay, now you've been looked at, you have to turn your cards back around.
And do I remember those values though?
Not allowed to remember them. Let's say for our purposes, the only things you're allowed to do is flip over cards and decide swap or not swap.
Okay, I'm gonna look at these two cards. Not swap. These two cards. Swap. These two cards. Swap them. These two cards. Yeah, not swapping those cards.
How did you know to go backwards?
Like, you're honestly asking me?
Yeah.
Like, I knew that.
You were remembering things, weren't you?
Wait, no, don't you?
You weren't meant to be remembering things.
I'm remembering that I've sorted up till that.
How can I trust you in this class if you're not going to forget things honestly?
Sorry.
Okay, wind that back, wind that back. Okay, let's do this again.
How do I even?
And this time, no remembering.
I don't. What?
Start again.
I'm so confused. So my goal is to sort from lowest to highest.
Yeah.
And I can't remember anything.
No. You can look at two cards at once.
Yeah. And then swap them.
Let's give it a go.
Okay, so I'm going to look at you guys. Yes, I'll swap your two cards. Now, I've forgotten that these two are sorted.
Yep.
Okay. I'm going to look at your cards. Okay, I'm not going to swap them. All right. Wait, do I remember if I've already checked a card?
So you can keep track of indices. So you can have a variable that keeps track of where you're up to.
Okay, sure. All right, I'm going to swap these two. Look at these two cards first. Keep them. I don't know how efficient this is, but sure. Yeah.
Make sure to use the microphone though.
Oh, sorry, I have to point. Okay, yep, keep you guys as is. Can I look at your card as well? All right, we're good. Now, I'm going to look at these two cards. Not swapping those two cards. I'm going to look at this card and that card. Oh, yes, let's swap. Okay, what? Okay, sure. Now, I'm going to look at...
Ooh.
Wait, do I have to look at this card again? No.
So what's your thought process?
We're good. All right. Oh, my thought process is I'm trying to figure out if I'm making decisions based off my memory or if they're like logical decisions in terms of not knowing. But I know that this is bigger than that.
So we ran into some trouble because what happened was we ended up doing a swap, and what your process was before, you were leaving this location stable.
Yeah.
But now that this location has changed, we probably have to restart our process again.
I'm not sure because if that card was bigger than that, but
Yeah, so you've made some inferences there. So you can keep going along.
keep going, yeah? Okay, I'm gonna look at this one and that one. Keep it. That one and this one. All right, we'll keep it like that.
Okay.
Okay, now from here, look at your card and your card. And swap. Look at your card and your card. Keep it. Look at your card and your card still. Keep it. All good. All right.
Why haven't you remembered everyone's names? I told you to remember them.
Yeah, that's true.
Oh wait, did I tell you to forget?
That's conflicting instructions. I'm sorry. All right, I'm gonna look at this card and that card. Swap them. Yep, your card and your card. Keep them. All right, last swap. Gonna look at these two cards and swap.
And are you done?
I think so.
Okay, so how are we going to check? Let's just do one final check.
Okay, sure. Sorry, Sasha. I'm gonna look at these two cards.
Okay, you can leave them turned around this time because we're just doing a check.
I'm just checking that that's bigger, and it is, and then I turn the next card. It's also bigger than the previous one. Turn the next card. It's bigger than its previous card. Turn the next one. It's bigger, and turn the next one.
And can we have a big round of applause for Honey? So you just created for us a whole sorting algorithm.
It's crazy.
Yeah. So can you explain to us what was happening as you went along? What happened to the overall order? As you progressed, what changed?
As I progressed, I think I tried to make sure each card was the lowest of all the cards after it, just by checking each card, comparing it to every card after it. And then once I've done that for the first card, I can like kind of forget it. Like I don't have to compare it anymore because I've already checked that it's the lowest out of the remaining.
Which means that the first card is in its final location, right?
Yeah, correct. And then I kept going and just checking all the cards. And if it was ever lower, then you swap it. And now you know that it's
It's the lowest of all you've seen in that run so far, right?
Exactly. So that was the algorithm.
And so then as you progress, what ends up happening to our overall array?
Yeah, it just sorts.
So we get a progressive sorting where we know the first one is in position, so we forget about it, and then we do all the swaps necessary to figure out what things should be in the second position, and then we go to the third position and figure out, okay, what is the thing that should be in the third position? And this type of sorting technique, I wasn't sure which one you were going to do. We started off with a different algorithm and then switched when we did the memory thing.
Wait, I'm not sure why the first algorithm was wrong, though.
Well, we can talk about the first algorithm after, but we ended up discovering what we call selection sort, which is the process of going through the array, figuring out what item is the right one to be in that location, and then moving on to the next location in the array, which was really, really exciting. The first one, the problem is that you went back and did a swap backwards in the array, but there wasn't really a principled reason to know why to go back at that point. Sure. And so it was a little bit confusing. Yeah. There are probably reasons you could have come up with, so you could say, well, let's go forward and do swaps and then go backwards and do some swaps and then go forwards and do some swaps, but that was a little less systematic. It was, however, close to an algorithm that we would have called bubble sort, which is go along, let's mix yourselves up again. And then turn those around so we can't see. The way the bubble sort works, which is another sorting algorithm, is to let's flip you two. And then if you're out of order, okay, you're in order, so just flip back. These two, you're out of order, so swap, turn them back around. You two, you're out of order, swap you, you two, you're out of order, you're in order now, okay, turn around, you two, you're out of order, swap. But now we're not sorted yet, so we go back at the start and we repeat this process over and over again until everyone is sorted. And that was the method that you were very, very close to using the first time, but we ended up in the end with our new technique, selection sort. So typically there are 3 different sorting algorithms that I see when students come down to the front. They're called selection sort, bubble sort, and insertion sort, and we don't learn all 3 of them every year. We only learn the one that our big brain figures out. So once more, can we have a big round of applause? And we are going to look, and we are now going to look at selection sort. Thank you very much. And you can have a which Skittles do you want? Wild berry, sours, or original?
Original.
Okay, original. And let's give you all of our volunteers for working so hard with the flipping can have whichever random packets you get.
Thank you.
There we go. And you can return your cards and return to your seats. So now we are going to play the game called, and here is something I prepared earlier, finally, because it does take a little more time to write a sorting algorithm. So the key thing that we're going to need to do at any point, so in our demo with Honey, Honey was looking for the lowest card. We're going to flip that and just do it the other way around, where at every given step of the way, we're going to look for the largest card, for the index of the largest card. So we're here going to have a function called index of largest, and the goal of this function is to go through an array and figure out what is the largest card. Once you've figured out what the largest one is, then you're ready to swap it with the point in the array at which we're up to. And then we have our function that's going to actually do the whole sort, that's going to combine everything together, and then a main function that's just going to drive it. So first up, let's create an array of values. It's going to be 1,000 values in this case. We're going to read in an array of that many numbers, print the array before and after, just so I can prove to you that it actually was sorted. Okay, let's look at index of largest. So it takes in an array, and it takes in a number n. Alex, you're holding the microphone. What is this number n that we're passing in, and why do we need it?
Okay, so we need to sort of track the size of the array as well, because C doesn't.
Remember, C doesn't track the size of the array for us, so we need to know how many elements we can actually go through. So this is pretty standard C code, or pretty standard programming code that you've hopefully all written kind of once in your life before to find the maximum value in a set of values. So keep track of what the maximum value is from the first element to the nth element. Figure out what the biggest one is. If the current element that you're looking at is bigger than the biggest one so far, save the index of what the biggest one was so far. So instead of actually saving the number that was the biggest, we're saving the index at which the biggest number could be found. So if the biggest number was in position 3, this function is going to return position 3. And the way we're doing that is just this comparison here, which compares the actual value of, let's say, the number that was at index 3 with the one we're currently looking at. You'll notice that in this function, we're actually starting I from 1, and that's because we assume that when we've seen nothing so far, we'll just assume for the start that the 0th element is the biggest one we've seen so far, and that makes sense. Because when you've seen nothing, the first thing you see is going to be the biggest, and that's why we're starting at 1. And then we have selection sort, which is actually really, really simple. For every position in the array, figure out what is the biggest item in the remaining part of the array, and then just do a swap with the biggest with the position that you're currently evaluating. So if we're figuring out what should go in position 0, find the biggest item in the entire remainder of the array and then swap it into position 0. Okay, now we should, actually this goes from the other side. It goes from the last item in the array back to the first I is starting at n. So let's say our array is of size 1,000. So start at position 1,000, figure out what should be at position 1,000, decrement I by 1. Now figure out what should go in position 999. Do that by finding the biggest remaining. Now in position 998, and so on and so forth. And by the time you get all the way back to position 0, you've repeated finding the biggest in the remaining, over and over and over again, and so by a process of induction, you will have sorted the entire array. Now let's see if I can compile this one. There we go. So you'll notice I actually did something a little different to compile it this time. I included not just one C file, but 2 C files. The reason I did this is because we're going to be testing multiple sorts throughout our semester, and there are a bunch of C functions that I'm going to want to reuse for all the different sorts that just perform some basic array operations. So if I open arrayops.c, I can see that there is a function that reads in an entire array of integer values, and there is a function that prints an array of integer values, and I've just pre-written these and I'm going to reuse them. And so to ensure that I can reuse them, I've done this combination of compiling both of the files together such that selection.sort.c can actually access those functions. And we'll talk more about how to combine functions across different source files a little later. So now let's run selection sort, enter as many as 1,000 values, so 3, 4, 8, 23. Let's give that a try. We can see before, that was the order of the values that I read in, and after, it has put them in sorted order. And that is all thanks to Honey, who gave us our wonderful algorithm for today. Ankit, let's get you a microphone.
What would the time complexity of the big O notation look like for a selection sort?
We are getting to that in the next segment of our lecture. So thank you for asking. If you go on Wikipedia, you can see a giant list of all the different sorting algorithms. Now, I want all of you to take very careful notes about every entry on this table, because every entry will be testable next week at the start of lecture. Got it all memorized? Ready? Okay, next slide. So the question is, Elizabeth.
Hello, sorry, just another question. When you're reading into an array in your function, did it matter that you didn't give it a number of values, or why didn't it matter that you didn't give it a number of values that could be evenly split into a square or a rectangle? You gave it
It wasn't doing a two-dimensional array. This is just one-dimensional sorting.
Okay, if you were trying to do a 2D one, would it matter if you didn't have a rectangle?
You would have to figure out exactly what you were trying to do exactly. I'm not sure what you mean by sorting a 2D array. You'd have to define that first, and then once you defined it, then we can discuss whether it needs to be square or not.
Yeah, right, thank you.
No worries. Other questions on that before we move on? Does anyone want to see the previous slide so you can write a few more notes on it? Okay, so the main point of that is just to show you that there are really a lot of different sorting algorithms in the world. It's a very deep field that we can learn a lot about. In fact, that was only the Wikipedia page on comparison sorting. There are other sorting algorithms too. So the question is which sorting algorithms should we use? And I think it was Ankit that just asked me, was it you that asked me what the time complexity is? Yeah, so one way to rate my algorithm is to figure out, okay, which is going to be efficient for my given use case. We'll talk a little bit about all the different desiderata for a sorting algorithm. That word means all the different things that one might desire from a good sorting algorithm. But let's start with insertion sort. This is what insertion sort looks like. So for every number that you encounter in the array, we figure out where the correct place is thus far out of all the positions that we have currently already worked with. So where should the number 2 go? It should go before 7, should go before 6, it should go before 3. Okay, what about where should the number 4 go? It should go before 8, before 7, before 6, before 5, but not before 3. Okay, that's the place to go. And so let's start by doing a basic analysis on this sort, and then maybe next lecture we'll come back and analyze selection sort specifically. I don't have pre-prepared analyses of all the different sorting algorithms, but I could just tell you what the big O is. Okay, so for this algorithm, what would be the best case? And let's go, we can go with Sam again.
Wouldn't the best case just be like 0 time and 0 swaps if the list is already sorted?
So if it's already sorted, what is the best place to put every item? So say you have the item in the ith position currently in the array. Where does that item belong if the list is already sorted?
In the ith position?
In position I. So every item is already in its place, which means how many swaps do you do for every item?
0.
You do 0 swaps, and how many comparisons do you do?
1.
You do 1 comparison, just to make sure that it shouldn't be further along in the array than it already is. So that's our best case. So we'll have to do 1 comparison for every item in the array. So if there are n items in the array, that's big O
of just n?
Of n, because we do 1 operation per item. There are n items, n times 1 equals n, and the function n is big O of n. Okay, so if everything is already in sorted order, there is nothing to do, and insertion sort is an algorithm that takes advantage of that. What about the worst case? Ella?
If it's in the opposite order.
So if it's in the opposite order, how many things are out of order?
All of them. Oh, but not the middle case. If the middle one's like in the right spot.
So there could be a middle one in the right spot.
Yeah, but otherwise everything's out of order.
So the most out of order we could be is such that the maximum number of items are actually inverted. So you want the maximum number of items to be in a place such that you'd need the maximum number of comparisons. So in this case, it is going to be reverse sorted order. That is going to be the worst case for this algorithm. And what about the average case? How do we figure that one out?
Like probably something like half of it is in order and half of it is in reverse order.
So it's very tempting to think, okay, what about the half and half version? But really the way to think about it is to think, okay, what are all the possible arrangements of this array? And we want to figure out, okay, what is the expected configuration of the array such that we can really average it out in some way between all the ones that are slightly better, all the ones that are slightly worse. So the average case is not asking what is the middle number of swaps you could have. It's saying for every possible arrangement of the numbers out there, what is your expectation of how this algorithm would behave? On average, if you run this, what should be the runtime behavior? And so this average case analysis often ends up being really, really tricky for algorithms, but at the same time ends up being one of the more important things that we need to know about an algorithm, because generally we're not going to get our data all in sorted order, and we're not going to get it all in reverse sorted order. If that's your expectation for your given use case, that that's going to happen sometimes, well, then you need to have a discussion about what algorithm is really right. But average case turns out to be really important because mostly in the world we don't have a very good sense of what our data is going to look like, at least with respect to the sorting algorithms we care about. So one thing, as I mentioned before, is the number of swaps that we're going to do is equal to the number of items that are inverted. So if 2 items should be swapped, that is equivalent to they're on the wrong side of each other, an inversion. So we can do some very fancy analysis, and I'm not expecting you to be able to replicate this analysis, but essentially we can say, okay, let's create one variable for every pair of possible inversions. So a possible inversion is element 0 and 1, should they be swapped? Should element 0 and 2 be swapped? Should element 0 and 3 be swapped? As in, are they on the wrong side of each other? And so you can figure out how many such variables you would need to represent all possible inversions of everything in the array. And if we calculate this out, we get n times n minus 1 on 2. And you can do the math fairly simply with just first year uni maths to count the number of variables up. This is just so that, for example, if you have a variable for element 0 and 1, you don't want to have a variable for 1 and 0 because that's equivalent. They're the same thing. It's asking the same question about the pair of elements, so that gets you the n by n minus 1 on 2. Now, for every pair of elements, if you're arranging them randomly, they could either be on the right side of each other or on the wrong side of each other. So that's a 50% chance, which, if we then apply that to the number of variables, that gives us n times n minus 1 on 4. Multiply that out, you get n squared minus n on 4, which is big O of n squared. So that gives us an average runtime for this algorithm of n squared. And in fact, for bubble sort, insertion sort, and selection sort, they all run average n squared. So there is going to be a difference in the real world because the algorithms do perform differently. We just talked about the best case for insertion sort, and it's going to be an exercise for you to go home and work out, convince yourself of the best case scenario and the worst case scenario for the other two sorts. But in practice, some of them will end up being better, and that's a matter of not just formal analysis, but also experimentation. This finally gets us to the point where we are ready to formally define big O in probably what I imagine is going to be the most formal mathematics that many of you will see in your first year. Now, I'm not doing this to scare you, it's more to give you a gentle introduction to something that might then be more useful later. So, here we go, drum roll. The formal definition of big O. Okay. Let's imagine all the functions in the world, every single possible function. So I want people to yell out functions. F of x, okay, another function. That's a computer function. Mathematical functions. Log of n. 2x squared. More functions. Come on, there are tons of you in the room. 6x. 4. Okay, 4 is a function, yep. More functions. Sine of x. You guys are picking really boring functions. What about like 3x to the 24 plus 7x squared plus 2x plus log x to the 7 plus, I don't know, there are a lot of functions out there. So what I want you to imagine in your brain is every single function in the entire world. You got that? Everyone imagining that? Every function? Okay. Now, our goal is going to be to put these functions in groups. And depending on which group they're in, that's how we'll label them. They're big O of something. So say, for us to say that something is big O of n squared, that means they're in the group of all the functions that are big O of n squared. So formally, for f of n to be an element of this set of big O of g of n, it's a set that contains lots and lots of different functions, it has to meet this complicated looking condition. So I'm going to read out the condition for you, and then I'm going to translate it. So this condition says f of n is an element of the set big O of g of n, which is just a name for the set. It's an element of that set if and only if there exists a number, n0, doesn't matter what that number is, and there also exists a value c larger than 0, such that for any n that you can pick that is bigger than n0, it is always the case that f of n is going to be less than the number c that you picked multiplied by g of n. Now that definition, reading it out like that, probably makes little sense to all of you. So let's boil it down a little more. If for all values of n larger than some threshold value, there's a multiplier c that's going to guarantee that the big function is always bigger than the smaller function. And what this is essentially saying, let's do one more level of translation, it's let's go past some threshold. Okay, let's imagine the function behaves weirdly at the beginning. Let's get past that weird beginning. Once we get past that weird beginning, if our function is consistently smaller than some other bigger function, then our smaller function is big O of the bigger function. And this complicated mathematical language is just a way of writing that down precisely. Ignore the beginning. The small function is big O of the bigger function, as long as at every point where you go along the function, it's still smaller. And to ensure that we're ignoring the constants, you're allowed to multiply the big function by whatever constant you like. Okay, who's still very confused? Okay, we have at least one hand, 2 hands. Come on, I don't believe that. There've got to be more of you very confused. Okay, so now we're going to do 1 or 2 worked examples that'll hopefully make this a little bit clearer. Is that a confused hand or a question hand? Question hand.
So like, are you essentially just like bounding the function f of n by c g of n to use that upper bound?
Exactly. So you're saying that f of n is always bounded by c times g of n, assuming that you ignore the very start of the function where f of n and g of n might behave weirdly. So for example, imagine you have a cubic function which goes down first and then up, and then at some point later starts going up a lot. This just says, you know, let's ignore those twists and turns at the beginning, as long as the cubic function, once we've gotten far enough, is less than a quartic function, then we can say a cubic is big O of the quartic, because the quartic is always going to be bigger than the cubic. So that is another way of saying n cubed is big O of n to the 4. Yes. Sam.
So a function could be big O of like multiple other functions that are bigger than it.
Yeah, it's big O of every function that's bigger than it.
Right, so how do you decide which? Do you just take like the smallest one?
Well, we're going to discuss that a bit, but you can say, depending on how good your proof skills are, you may only be able to prove that it's big O of n to the 4, even though it's actually big O of n to the 3 if you had a better proof. So you want to give the best proof you can, giving it the tightest bound, but if you can't, it is sometimes acceptable to leave that higher bound. And in fact, this is a lot of what theoretical computer scientists do. They say, well, I believe that this function is probably big O of n squared, but right now the best proof that I have is it's big O of n cubed. And so I'm going to spend the next 20 years of my life looking for that proof, but until then the best proof we have is the n cubed one.
Right.
Yeah.
Before, when we were talking about the insertion sort, we talked about a best case, and we said it was big O of like n. But when we define big O of n, we've defined it as the worst case necessarily, right? So is there a mismatch there?
So this isn't defined as the worst case. This is just defined for some function. And it depends what that function is. Is the function f measuring the best case? Is the function f the function that measures the worst case? Or is the function f a function that measures the average case?
Okay.
So it means for whatever function you're looking at, whether that's the average case function, the best case function, or the worst case function, you evaluate each of those independently.
But it still ends up being the upper bound of.
Yeah.
Okay.
But it might be an upper bound on the worst case.
All right. Okay, that makes sense. Yeah.
More questions so far before we moved on to a worked example? Okay, worked examples it is. So this is pronounced like this big O notation. You pronounce it big O of g of n, or you can also say the function f is of order g of n. And as you get to if you continue with computing, which I hope many of you do, you'll also learn of definitions that are a bit stricter than this that allow you not just to give upper bounds, such that it's big O of n to the 4, n to the 5, n to the 6, n to the 7, but give you tight bounds as well, such that you can say this is what we call big theta of and big omega of, which are upper bounds and tight bounds respectively. Okay, just one note for this when we're about to do the proofs. Once you pick your value of n0, which is the threshold after which the function starts behaving normally, and the value c, which allows you to multiply the function g to ignore the constants, once you've picked those, you have to stick with them for the rest of the proof. You can't change them midway through the proof, which is also a problem that I see with students sometimes. Now, I will say that in previous years, we have not actually tested these proofs, tested your workings of the formal proofs, because we haven't given you enough practice. It is my dream every year to give students more practice, but unless you start experiencing more practice with this in semester, you won't be tested on doing these proofs yourself in any significant fashion, even though you will have to replicate some of the underlying reasoning. So you'll have to be able to still identify what something is big O of, but unless we give you practice, and that'll be very obvious to you if we do, you don't have to replicate all these proof steps. So don't freak out too much. Okay, so the intuition here, again, to repeat it one more time, ignore small values of n. So like f of 1, f of 2, f of 3, probably don't care about those because the function might still be behaving weirdly at this point. Pick after a while where the function's behavior starts to stabilize, and only at that point compare it to g of n. So let's start with a really easy example. We want to prove that 2n, the function f1, which is 2n, is big O of n. So there is some threshold after which the function 2n is always bounded by c times n, because our function g is n, and so that multiplier c is what's going to be really important to pick. So I'm going to say that our threshold is going to be the number 1, and our value of c will be 2. And I know these in advance because I've worked out how this proof is going to go. If you were starting from scratch, you would have to be intelligent and use clever guesses and intuition about how these proofs work in order to pick these values. So for now, just trust me, we're going to start our threshold n0 equal to 1 and our value of c equal to 2. So here is the next step of our proof. We want to prove that f of n is less than or equal to 2n for all n greater than 1. And the reason I wrote 2n over there is because the value of c I picked is 2. Now this is going to be pretty trivially true. The function 2n is definitely less than or equal to 2n for all n. So that is the complete proof. We have proven that f1, which is 2n, is bounded by 2 times g of n, which is the function n, for all n greater than or equal to 1. And there's our entire proof statement. Now it would also work just as well if you picked n0 equals 2 and c equals 3, because then we would get 2n is less than or equal to 3n for all values of n greater than 2. That works as well. But you can see that I picked these values to be particularly tight. Questions on this one? Now let's let a function that we want to provide an upper bound for. This is going to be 15n plus 27 root n minus e log n. And we still want to show that this is still big O of n. And I am now going to hopefully do this proof, and please catch me out on mistakes because I'm not a very good mathematician. So the function we want to bound is the following. And we want to show that this function is less than c times n. And so I'm going to, ahead of time, because I'm very smart and I've done this proof before, we're going to pick our threshold as n as just 1, like we did in the previous one, but this time c is going to be 42. So what I can do over at the top here, I want to show that this is less than 42n. Okay, so the first thing I can do is I can say that this function over here is definitely upper bounded by the following function. So 15n plus 27n minus e log n. So when I remove the square root makes the function smaller. So if I remove the square root, that makes the function bigger, which means that it must be true that this relationship holds. I've made the function bigger. There is no possible world in which taking the square root of something is bigger than not taking the square root of something for n greater than 1. Yeah, that is why I have my threshold over here. Right? So now I'm guaranteed that this relationship holds. So if I can prove that this is still smaller than 42n, then I know that the original thing that I started with is also going to be smaller than 42n. Okay, next step. Let's divide both sides by 42. and then the relationship will still hold. On 42, on 42. So someone tell me what happens in the proof now? Not unkit. Come on, this is like high school maths. What is 42 divided by 42? So that's just going to be n over there. And then what happens on this side? What's 27 plus 15? 42. Okay, we're making some progress. So now we have 42n over here. And now what am I probably going to do? I'm going to split it. So I'm going to do 42n on 42, which is the same as n minus e log n on 42. And it doesn't matter what value e is. And now what do I do? Come on. Typical proof for high school. I'm going to move the n over to the other side, or I'm going to move the e log n. Let's do that. So I move the n to the other side, minus n, which gives me 0. And now, is it always the case, when n is greater than 1, that this value on the left-hand side is going to be less than or equal to 0? Yes, we know that because log gets you a positive value, and as long as e is non-negative, we have now proven, and we know what e is. E is a positive number, so therefore the overall proof is completed because we can guarantee that this is less than 0. Therefore, we know this original statement is true. We know our function f, or f2, is always bounded by c times n, and so f2 is, finish the sentence, f2 is big O of n. So big O, as we mentioned before with Sam, does not provide a tight bound. There are always bigger functions, g of n, of which it's big O of. Okay, now we can do one more proof in this kind of sequence. I hope I get a little more audience interaction this time. Let me just copy it down. Okay, first step in the proof. What do I do? Garv, you've got the mic.
You can multiply f2 by f1 to get what f3 actually is.
Yep, so multiply f2 by f1, so I get 30n plus 54 root n minus 2ne log n. And then what I want to do is I want to show, for certain, I want to prove this statement that this is less than 84n squared. Oh, I missed my squares.
Yeah.
Oops. Yeah, I'm fixing that up. Half 3 on 2. Sorry about that. Thanks for catching my mistake, whoever said that. Okay, now we can do exactly the same thing that we did before. 4 on 2n is bigger than 3 on 2n. So we know that that the proof must still work if we do 30n squared plus 54n 4 on 2, which is the same as n squared, minus 2ne log n. So 30 plus 54 is 84. So I have 84n squared on one side, 84n squared on the other side. So 2ne log n is less than 0. And we've said that n is greater than 1. If n is greater than 1, this must always still be negative. We've completed our proof. We know that the overall function is big O of n squared. Yes, Sam?
How, again, could you just guarantee that making 54n 3 over 2 into just 54n squared doesn't make it so much bigger that it goes over the boundary of 84n squared?
We don't know. That's what we're setting out to prove. So the fact that I've tried this and seen that indeed it is less than 84n squared
right, okay.
is the proof.
Right.
So one key thing to remember is that big O of g of n contains all the functions that it's a set of things and contains all the functions that are smaller than it. So n squared contains x, it contains 2x, it contains 2x plus 5, 2x plus 7, etc., etc. We're going to make it easier to think about our classes by just always thinking about like big O of n squared instead of thinking of like big O of 3n squared or big O of 3n squared plus 5. Even though we could use those in our proofs and they'd probably work out okay, it's going to make our lives difficult, and the whole point of big O is to allow us to throw away those constants and the terms that don't matter and only focus on the high order terms, the terms that make a big difference to how the algorithm behaves on larger amounts of data. What this does mean, though, is that if you're actually dealing with a lesser amount of data, the big O might not be an appropriate tool for you. It might be the case that the big O behavior of the algorithm is fast, but the actual behavior of the algorithm on your data is not as fast. And that's part of learning really good design of algorithms, is understanding both the theoretical side and the practical side. So this is going to mean drop some constants, drop extra terms, and make big O of n of g of n contain as few functions as possible. Give the tightest bound that you can to be the most useful. So fewer functions is going to be equivalent to a tighter bound. And we're going to use this notation throughout the rest of the semester to compare algorithms, best case, worst case, and average case. Thank you all very much for another long lecture session. Enjoy the rest of the week, and I will see you soon.